Hi everyone, this is our second and final video on data compression. So we begin by recalling an important theorem that we discussed at the end of the last video. The upshot of the theorem is that if you have a well-behaved stream of symbols and you want to encode this stream, instead of encoding individual symbols, it's more efficient to encode blocks of symbols, like maybe blocks of size 2 or blocks of size 5. And this theorem is telling us that we can choose the block size n and corresponding prefix-free code on those blocks so that the average number of bits per letter, that's this, is as close to the source entropy h as we like. So you might recall that in the previous theorem, we used the fact that we had learned about prefix-free codes from a previous probability distribution. So that fact is that if I have an alphabet, we can find a prefix-free strings of length n with probability distribution, in this case Pn, I can find a prefix-free code whose average code word length is less than the entropy of the distribution plus 1. Now, maybe you're remembering that to obtain that result, we could use the Shannon-Fano rule, or we can use a Huffman code, which is even better. However, there are drawbacks to both of those methods. First, the Shannon-Fano rule tells us the parameters y1 through ym, these being the lengths of each code word, but it doesn't directly give us a code. Remember, once we have those lengths of the code words, then we need to do this tree construction in order to produce the code words themselves. Now, on the other hand, we could try Huffman, which is an optimal code, but it requires us to determine every single code word, even if we don't need all of them. So here I'm asking you to remember now the process to produce a Huffman code, right? Where we produce this tree from the probability distribution and then work our way up to produce the code. And we have to, at the end of the day, write down every single code word, even if we don't need them all. So there's another option now that we've not yet considered that we're going to use, and that's the idea of arithmetic coding. So arithmetic coding, it's different from Shannon-Fano, it's different from Huffman, and the reason it's called arithmetic is because it's going to involve base 2 representations of certain numbers. So before we can do any arithmetic coding, we need to learn a few things. So the first thing that we're going to learn about is the dictionary order on strings. So we begin with an alphabet S, and we're going to put an order on its elements, meaning there's going to be a smallest one and then a next smallest and so on and so forth up until we have a largest element. Now the order on strings of length R, called the dictionary order, works like this. So we suppose we start with two strings, X and Y, that are different strings, and in order to compare which one is bigger or smaller, we're first going to identify the first or smallest index I where X sub I differs from Y sub I. Now, if X sub I is less than Y sub I, then the string X will be declared to be less than the string Y. Meanwhile, if X sub I is larger than Y sub I, here again in the order on S, then string X will be judged to be bigger than string Y in S sub R. Okay, well, if this strikes some chord of familiarity, it should, because this is the very same process that we use to alphabetize words in the English language, and therefore, that's why we call this order the dictionary order. So here we have an example. We have a simple alphabet consisting of 3 letters, A, B, and C, and we're going to impose an order on S where A is less than B, which is in turn less than C. So we're going to compare some strings in S3. So that means that we're going to be looking at strings of length 3 and comparing them. So let's first start with, say, x equals BAC and y equals ABC. And we want to know, which of x or y is bigger. So remember that the process asks us to identify the first place, beginning from the left, where the strings differ. And that happens right at the very beginning, that the strings differ. And now that I've identified that place, I compare those two objects. That is, I compare A to B. Now I know A is smaller than B in my order on S, and therefore my string Y is going to be less than string X in the dictionary order on S3. Okay, well, let's try a couple more. So how about if X is equal to AAA and Y is equal to AAC? Well, we start from the left and we look for the first place where they differ. So they're the same here, they're the same here, and then they finally differ here. Once I've found the first place they differ, I compare the individual letters in the alphabet, A and C, and I know that A is less than C according to my order on S. And so that tells me that X is less than Y. Okay, and now maybe just one more, because it's fun. What if we have, I don't know, X equals AAB and Y equals ABA? So here again, we start from the left, we look for the first place where they differ. They're the same here, but they differ here. And because A is less than B, we conclude that string X is less than string Y in the dictionary order. Now notice up here in the example statement, we listed this total order on S. We could also do the same thing now for S3. We could take all of the strings of length 3 and list them in order from smallest to largest. Now you might observe that this string here, this particular value of X, that's our smallest string possible in S3. And then what would the largest string be? Well, it would be CCC. The next thing we need to know in order to produce an arithmetic code is the notion of a cumulative probability function. All right, so here's how it works. We've got strings of length R on alphabet S, and we're going to assume that there's an order on S that induces the dictionary order, which we just talked about, on strings of length R. Now, the cumulative probability function, what it does is it's going to assign the value 0 to the very smallest string in S sub R. And then for all other strings, if you want the cumulative probability function of that other string, you just add up all the probabilities of the smaller, strictly smaller strings. Okay, so there's an example is definitely warranted here. Okay, so here we have an alphabet S consisting of X, Y, and Z with this order on S. And we have this probability distribution P2 on strings of length 2 over S. So we're going to do two things here. We're going to put the elements of S2 in dictionary order, and then we're also going to give the cumulative probability function, A. All right, so let's take our elements, our strings of length 2, and put them in order. So the very smallest one would be XX. And then if we go next in the dictionary order, we should have XY, and then XZ, and then YX, and YY, and YZ, and then finally ZX, ZY, and ZZ. Okay, so those are our strings of length 2. And now what we're going to do for each of those strings, we're going to compute the cumulative probability function. Okay, now, so we first compute A of the string XX. So XX is the smallest string. Right, XX is the smallest string in S2, and so we assign the value 0 to that. So now when I take A of XY, I'm going to be adding up all of the probabilities of the strings that are less than the given string XY. Now here, the only string that's less than XY is XX, and its probability from the table is 0.21. Okay, so next I want to find A of the string XZ, which means I am to add up the probabilities of all of the previous strings, that is of XX and of XY. So the probability of XX is 0.21, the probability of XY is 0.08. If I add those together, I get 0.29. And then I go to YX, and again, how do I find A of YX? Well, I'm going to add up the probabilities of all of the previous strings. So that's going to be XX, XY, and XZ. So that would be 0.21 plus 0.08 plus 0.02, which is 0.31. So we continue along our way here, and we obtain these numbers for this cumulative probability function. So I think it would be worth your while to make sure that I've done this correctly. That is, for instance, for say ZX, make sure that if I add up the probabilities of all of the preceding strings, not including ZX, that I wind up with 0.81. So now we're ready to describe the arithmetic coding process. The idea here is to produce a binary code, and we're going to do it by producing binary expansions of certain numbers. Okay, we start with a stationary source and a probability distribution PR on strings of length R. Throughout here, X is going to denote a string of length R. Now here, we're also in the background assuming that there's an order on S that induces the dictionary order on strings of length R. And that means that, this cumulative probability function can come into play. Okay, so first ingredient is this object M sub X. So that's going to be the least integer such that 2 to the M sub X is bigger than or equal to the reciprocal of the probability that X occurs. Next, we form N sub X, And that's not too tough to form. We just take m sub x and add 1. Now this n sub x is going to be important to us because that's going to be the length of the code word that we associate to x. Now once we have m and n, we're then ready to form this number t. So t sub x is going to be the unique integer satisfying this inequality. So in the middle, we're going to take 2 to the n sub x and multiply it by the cumulative probability function evaluated at x. And then t sub x is the unique integer satisfying this inequality, where really, so there's an error here. This inequality should be a strict inequality. Okay, now once you have found t sub x, then you're almost ready to produce the code word associated to x. So what you do is you take your t sub x and you find its base 2 representation right here, and you make sure that it is of length n sub x, right? Because remember, we want our code word to be of length n sub x. And that's the code word, just this base 2 representation of t sub x of length n sub x. Now, one good thing about this whole process is that you can compute the code words as you need them. And while the description here is given for binary codes, the same ideas can be used for other types of codes too. Now we give an example of an arithmetic code for strings of length 2 on the alphabet that was given in the previous example. So remember, in our previous example, we had this simple 3-letter alphabet XYZ. And we were also given a probability distribution P2 on strings of length 2. Now I'm not going to repeat that probability distribution here. If you need to see it again, you can always pause the video and go back to look at it. Okay, so in this table we have, gathered all of the ingredients that we need for our arithmetic code. So first thing we're going to need is the values of the cumulative probability function for each of these strings. Now remember, XX is the smallest string in S2, and the cumulative probability function of the smallest string is 0. So then we compute A of xy. Well, that's going to be the sum of the probabilities of all the strictly smaller strings. The only strictly smaller string here is XX, and its probability was 0.21. So now we can continue to fill in these values just as we did on the previous example. Okay, next it's time to compute these values of m. So you'll recall maybe from a previous slide, why don't we compute, for instance, m of x sub z. So how do we do that? Well, you recall from a previous slide that we want 2 to the m sub xz to be bigger than or equal to the reciprocal of the probability that xz occurs in our stream of symbols. And now if you look back at the probability of xz on the table that occurs on a previous slide, you should get that it's 0.02, and the reciprocal of 0.02 is 50. So I want 2 to the m sub xz to be bigger than 50. And so that says that m sub xz should be 6. Right, so we want the smallest number where when we raise 2 to that power, we get something bigger than 50. Okay, now you can do a similar calculation all the way across the board here if you like. You get 3 and 4 and 4 and 2 and 7 and 7 and 6 and 3. Okay, it might be a good idea for you to pause the video and double check that I have done those numbers correctly. So now it's time to compute the values of n. Remember, those values of n are going to be the lengths of our code words. And luckily, it's pretty easy to compute the values of n. All we need to do is add 1 to the values of m. So we get a 4 and a 5 and a 7 and a 5 and 3 and a couple of 8s here and a 7 and a 4. Okay, now it's time to compute these numbers t. Right, so remember, and in fact, why don't we do a specific example? Let's look at this x sub z again. Remember, t sub xz xz minus 1 needs to be less than or equal to 2 to the n sub xz times a of xz. And that needs to be strictly less than t sub xz. Now this number in the middle, you can compute it, right? So this is going to be 2 to the 7th times 0.29. So we're going to go ahead and compute what that number should be. In fact, if we look at that, in fact, let's just do it right now on the calculator. 2 to the 7th, it's 128 times 0.29. So I get 37.12. Now t sub xz is got to be an integer. And so that suggests that this number should be 38. So we put that number here. And now if we wish to, we can do this for all of these other slots in here. So you should just double check me to see that we get 0 here, 7 there, 10, 4, 205, 208, 105, and 7. Okay, now what we want to do is compute the code words. So first, let's clear some space down here. All right, now to form the code words, what we want to do is write down all of the numbers t in binary, making sure that our expansions have length n. So if I write 0 in binary and I use a representation of length 4, that is given right here in the n information, this should be my code word. Right? Remember, C of u is going to be the binary representation of t sub u of length n sub u. Okay, now, next we have the code word for xy. So I want a binary representation of 7 that is of length 5. So that would be 0, 0, 1, 1, 1. Next, I want a binary representation of 38 of length 7. So that's going to be 0, 1, 0, 0. And then 1, 1, 0. And then a binary representation of 10 of length 5 would be 0, 1, 0, 1, 0. And then a binary representation of 4 of length 3, which would just be 1, 0, 0, right? It would be 0, 1, 0 1s, 0 2s, and 1 4. Binary representation of 205 of length 8. Okay, so we're going to try and cram this in here. It's 1, 1, 1, 0, 0. 1, 1, 0, 1. So that's 1, 1, 0, 0, 1, 1, 0, 1. Binary representation of 208 of length 8 would be 1, 1, 0, 1. And then 4 zeros. Binary representation of 105 of length 7 is 1, 1, 0, 1, 0, 0, 1. And then finally, binary representation of 7, this time of length 4, which would be just 0, 1, 1, 1. Okay, so these objects are the code words that we seek in our arithmetic code. Like this one, for instance, is the code word that we would associate to YY. Now, one thing that might be good for us to just check is whether this is a prefix-free code, right? We've not given any sort of justification that this is prefix-free or whatever, but if you look at it, you can check that it's prefix-free. Another thing that might be good to know is what the entropy of this distribution is. So we could go ahead and compute this. It turns out to be about 2.387. We could also compute the average code word length for this code, which is about 3.97. So maybe this average code word length is not quite as close to the entropy as we maybe would like, but it turns out that it's close enough, as we shall discuss in a moment. Here we have a few theorems about arithmetic codes that we will discuss but not prove. I'm asking that you will read the proofs in your book. Okay, so throughout here, S is going to be an ordered stationary source with probability distribution PR on strings of length R. The first fact is that arithmetic codes are always going to be prefix-free and therefore always will be uniquely decodable. So it's not a fluke that the code that we produced on the previous slide was prefix-free. Next, the average code word length for the arithmetic code is always going to lie between the entropy of the distribution and the entropy plus 2. Now, you might recall how that compares to Shannon, Fano, and Huffman, right? For those codes, average code word length is between the entropy and the entropy plus 1. So here, the result about average code word length for arithmetic codes is not as good as for Shannon, Fano, and for Huffman. However, there's an advantage here in that we can create code words piecemeal. We don't need to create all of the code words in order to have some of them. And further, this is really not too bad, because if I want to compute the number of bits per symbol, I want to now take this and divide by R. So if I divide by R all the way across the inequality, well, on the left, what happens? Well, this is tending towards the entropy of the source. This, of course, is the average number of bits per symbol. And here, this, of course, is becoming the entropy. What about 2 over R? Well, 2 is a little bit bigger than 1, But that's okay, because if I let r get big, 2 over r gets small, just in the same way that 1 over r would get small. So this result here in the second block, this one right here, is in essence just as good as the +1 example was for proving this fundamental theorem about coding in blocks.